Today we're talking about a very important topic in weather, and that's humidity. Humidity is just a measure of the amount of water vapor in the air. It's not what usually the weathermen talk about. They're talking about relative humidity, even though they might say, oh, it's really humid today, or the humidity is this. They're talking about relative humidity, which we're going to talk about on the next slide. On this first slide, though, we're introducing the topic of humidity, and humidity is just a measure of the amount of water vapor in the air. So it's how much water is in the air, determined by the air temperature and how much water is available. And we're going to see again this more on the next slide, but you should be able to see that the warmer the air is, the more water it can hold. Okay, so the warmer the air is, the more water it can hold. Because hot air expands, there's more room for water. When you cool air, it contracts, there's less room for water. And we'll see this more on the next slide. So now we are talking about relative humidity, and this is what we usually hear on the weather forecast. The definition starts off the same as humidity. It was a measure of the amount of water vapor in the air, but now we compare it to the amount of water vapor the air could hold at that temperature. So it's a measure of the amount of water vapor in the air compared to the amount of water vapor the air could hold at temperature. Because it's a comparison, when we do it, we're going to get a percent for our relative humidity. So let's do an example. At 15 degrees Celsius, 1 meter cubed of air can hold how many grams of water? So let's look at the chart. So 15 degrees Celsius would be right here. Go up, go over, kind of straight. Let's say about 12. Okay, so it can hold 12 grams of water at 15 degrees Celsius. Suppose it only has 4 grams of water in it. What's the relative humidity? So relative humidity, again, we think of our definition, it's a measure of the amount of water vapor in the air, that's 4, compared to the amount of water vapor the air could hold at that temperature, 12. So 4 over 12 is about 33%. So in this case, it would be 33% relative humidity. It would feel pretty dry. Okay, 33% is fairly dry. There's a lot more room in the air to soak up water. Let's look at this picture up here. Let's start off with the picture on the right. 30 degrees Celsius air can hold this much water vapor. Let's say there's only this much water vapor in it. It is 28% filled. If we take this air and we cool it down, so we cool it down 10 degrees, now it's 20 degrees Celsius. Look at what happens to the air. The air shrinks. Okay? As the air cooled, it contracted. The water vapor, though, didn't contract. The water vapor is still the same volume. So now it's occupying 52%. So the relative humidity has increased even though we didn't add any water. It increased because as we cooled the air, cooler air can hold less moisture. If we cool this air even further, from 20 degrees down to 10 degrees, we see now the water vapor is completely filling all the space in the air. So the relative humidity is 100%. What we're going to see, we're going to call this, kind of in the next couple slides, we're going to say that this is saturated. Okay, 100% relative humidity is saturated. What that means is the air cannot hold any more water. It is completely filled with water. What if you tried to add more water into it? Well, it wouldn't be absorbed. Okay, it's completely filled with water. The temperature at which it is completely saturated, so in this case 10 degrees, that's called the dew point. And we're going to see this again on a slide coming up in a little bit, just as a little preview. The dew point is the temperature at which the air is saturated. Well, what do you think would happen if we now cooled this air, let's say 10 degrees, we cool it down to 5 degrees. What do you think is going to happen? It's going to squeeze some water out. It's going to have to squeeze some water out because cooler air can't hold as much water vapor. So still looking at this chart and kind of thinking about what we set up here, let's talk about a desert, a really, really hot desert. Does this graph explain why they usually don't get any rain? Yes. So if we look up really high temperature, what do you see about air at really high temperature? It can hold lots and lots and lots of water. Well, in a desert, are you going to have this much water available to evaporate into the air? No. So it's not going to rain because it's never going to get saturated. Does it explain why we don't really get much snow or rain in really, really, really cold places? Yes. If you look down here, really, really cold places, how much water can the air hold? Well, like nothing. So if I can't hold any, we're not going to really get much snow or rain because it cannot evaporate the water vapor into the air. The air is so small. Think of this trend again. If we keep on going, we go down to like negative 10 degrees. The air is so small that it just can't fit enough water vapor in it to make any significant rain or snow. So raining, snowing, all that stuff deals with humidity. I talked about saturated on the last slide. Here's kind of it written down. When the relative humidity reaches 100%, the air is saturated. Okay? It is completely filled with water, like we saw in this picture. Okay? It cannot hold any more water. So any cooling of the air will cause what to happen? So again, if I cool this air, it's going to squeeze the water out. So condensation will happen. If this is up in altitude, we're going to make a cloud. If it's on the ground, we might make dew or frost, which we're going to talk about here in a second. If it's maybe, let's say, a glass like this, we're going to have sweat on the outside of the glass because we have ice cubes in here cooling it. So dew point is just the temperature at which the air is saturated. Okay, so when relative humidity reaches 100%, the air is saturated. The temperature at which that happens is called the dew point. So dew point is a temperature. Okay, dew point is a temperature. And it's the temperature at which the air is saturated. So relative humidity 100%. Frost, we'll talk about this here in a second. I'm going to do a little demonstration, so I'm going to stop the screencast here and do a little video to show a little demonstration. And you kind of think again about this glass. I have water in the glass. I put ice cubes in it. It's going to cool the glass. So the air on the outside of the glass gets cold. You know, hopefully you remember, what happens to air as it cools? It contracts. Cold air can't hold the moisture, so it's going to make these little beads of sweat on the glass, and then they're going to drip down, and they're going to go onto your mother's nice antique table and make a water ring, and you're going to get in huge, huge trouble. I may know that from a little bit of experience before I knew what was happening. So that's why you need to have a coaster under your drink. Okay? The glass gets really cold because of the ice, so it cools the air next to it to its dew point temperature, so the water condenses out onto the side of the glass. Okay, before I show you a little video, I want to also show you a video about a psychrometer and how it works, so I just want to talk about this. So we said what relative humidity is. Well, how do we measure relative humidity? We measure it with a psychrometer. So a psychrometer is just a device to measure relative humidity. And there could be a fancy chart like this, or we're going to use an easier chart like this. We're going to use this in class, and I'll use it to show you. Looking at the psychrometer here, you see it's a very simple thing. You have a dry bulb thermometer and a wet bulb thermometer. And again, I'll show you that in the video here in a second. Let me go on to the next slide, and then I'll show that to you.
In this little video clip, I want to show you two things. I first want to show you about dew point and saturation, and then secondly, I want to show you how to find relative humidity. So like I said, we're starting with this idea of dew point and saturation. And what I have is a sponge, and this sponge is going to represent an air parcel. I have a little bit of moisture in the sponge, it's certainly not filled with water, so it's not saturated. I can tell it's not saturated because if I take some water and I dump some water in, it can hold it. So it wasn't completely filled, it wasn't saturated. Eventually, if I pour more water in, it's going to reach a point when it is saturated. Not yet, but a little bit more. Okay, now it's saturated. Any water that I add forces other water to come out. So it is completely filled. It's saturated. What if this air cools? The air is going to contract. Okay, as air cools, it contracts. So it's going to start to contract, and as it does so, it's going to squeeze out some water. Now, let me squeeze out a little bit more water and say this again. So, this air parcel has a little bit of water in it. It's certainly not saturated. Let's say it's a spring day or fall day, the sun's out, fairly warm outside, but it's getting closer towards night. And at night, the temperature is going to drop. As the temperature drops, the air is contracting. It's squeezing. As it contracts, the relative humidity is increasing. I have the same amount of water vapor in a smaller volume of air. So the relative humidity is rising, 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 until it gets to a point when the relative humidity is 100% and the air is saturated. So it gets to that point, there we go. Any more contraction or any more cooling is going to cause the water to be squeezed out and form dew on the grass or the car or whatever. It had contracted, so it had contracted until it was holding all it could hold. It was 100% full, it was saturated. Any more contracting, any more cooling, means the water has to be squeezed out. It's going to form dew. Well, what if the dew point, remember the dew point is the temperature at which this happens, so what if the dew point is below freezing? Well then, when it squeezes it out, it's not going to squeeze it out as a liquid, it's going to squeeze it out as ice crystals, and it's going to be frost. So dew point is that temperature at which the relative humidity is 100%. In another lesson, we're going to talk about clouds and how clouds form. And it's the similar idea, except we're not going to have the contraction, but as we raise air up in the troposphere, the temperature decreases. So as you go up in the troposphere, the temperature decreases. That means the air can hold less and less moisture. So eventually it's going to reach an altitude where it's saturated 100%, and it's going to form a cloud. Okay, so there's going to be an altitude when it reaches its dew point. Okay, so dew point is the temperature at which it's saturated. Okay, so that's what I wanted to show you that. And so the second thing I wanted to show you was I wanted to demonstrate how to find relative humidity. The instrument that you use is called a psychrometer. And here's an example of a simple psychrometer. This is called a sling psychrometer because I'm going to sling it around. It's a pretty simple device. It's composed of a dry bulb thermometer. So on this side is a dry bulb thermometer, a thermometer with nothing on the bulb. It just reads the air temperature. So in this case, it says the air temperature is, it looks like 25 degrees. So it's 25 degrees in the classroom. That's the dry bulb. The other side has a piece of cloth on the bulb. And what we're going to do is we're going to get that bulb wet. So I have some room temperature water, dip it in there, get that cloth nice and wet, take it out, and now I'm going to sling it around. As I sling it around, some water flies off, but more importantly, the water starts to evaporate. As the water evaporates, what happens to the temperature? It drops. The temperature cools. You've all experienced this. Okay, when you get out of a swimming pool and the wind blows, you feel incredibly cold. You rush to get a towel to dry off. The reason that happens is to change water from a liquid to a gas, it takes energy. So it's sucking that energy out of you, or out of the bulb in this case, so it's going to read a lower temperature. So I spin this around and around, I'm getting bored with this, so I would say I'm done. So now hopefully the temperature is a little bit lower. And you look at it, and you see the wet bulb temperature now is 18 degrees. So it's gone from 25 degrees down to 18 degrees. So it's a pretty big difference. Lots of water evaporated. I'm going to go to the computer and I'll show you what this means and how to calculate in a second. But first I'm going to leave you with two questions, and I'm not going to answer it. You can answer later. What if I sling this around and around and around and no water evaporated? What would that mean about the relative humidity? Or what if I slung it around and around and around and lots of water evaporated really quickly? What would that mean about the relative humidity? And what would the thermometer read? So if no water evaporated, what would the wet bulb read? If lots of water evaporated, what would the wet bulb read? Okay. So you can think of those questions. All right, let me go show you how to calculate.
So now we're back looking at our relative humidity chart. And I just showed you with the sling cyclometer how it works. And we have our numbers. Remember, our dry bulb temperature, so dB dry bulb, was, I think it was 25 degrees Celsius. The wet bulb was only 18 degrees Celsius, so a lot of water evaporated. So first thing you do, dry bulb was 25, so you see dry bulb temperature, find 25. It's not there, but it's halfway between. We can make it work. Okay, we'll figure it out. Then we need the difference between the wet bulb and the dry bulb. So subtract these two, and you get a difference of 7 degrees Celsius. So a difference of 7, go down to where this crosses over, and it looks like we're going to be between 49 and 51, so the relative humidity in the classroom was 50%. That's all you do. Okay, that's all there is to it. You're just using your dry bulb and the difference between your dry bulb and your wet bulb. And again, think of those questions that I said. What if no water evaporated? What if a lot of water evaporated? What is the wet bulb going to be? What's the dry bulb going to be? And think about what would happen on here. Okay, the last thing I want to talk to you about is the heat index. And it's an important topic. And you might have heard this saying, it's not so much the heat, it's the humidity. Okay, so we'll talk about what that means. So basically, it's how hot the heat-humidity combination makes it feel. So let's say that it is 100 degrees outside. So this is Fahrenheit. If you want to do Celsius, you can see the Celsius temperatures on this chart down here. So it's 100 degrees Fahrenheit outside, but it's 50% relative humidity. You trace it down, go over, it's going to feel like 120 degrees. Why does it feel hotter when there's a higher humidity? Well, we got to think. What does your body do to cool itself? It sweats. So when you have sweat, the sweat evaporates. We learned with the wet bulb, when water evaporates, it's a cooling process. So the sweat evaporates from your skin and it makes you feel cooler. But if we have a high humidity, can the sweat evaporate very quickly? No. So you feel hotter. So let's get an even maybe better example. Let's say it's down to 95 degrees, so not that hot. But it's 80% humidity. When we go down, it feels like it's 136. Okay, so we're looking at that one. So what does your body do to cool itself? It sweats. At 80% relative humidity, does that sweat evaporate very easily? No. So does your body cool? No. So what does your body do? It sweats some more. Does that sweat evaporate? No. So what does your body do? Sweat some more. Does that evaporate? No. So you get this keep process where you can get dehydrated and you can suffer from heat exhaustion and also heat stroke. Your body temperature is going to rise higher and higher and higher because your sweat won't evaporate, so it won't cool you. So this heat index is really, really important if you're outside playing football or really anything else, especially if you have pads on, makes a huge difference. Does it work the other way? People say, oh, Arizona, it's 120 degrees, but it's a dry heat. Does that really matter? Well, let's look. 120 degrees, but 0% humidity, it feels like 107. It does matter. Okay, it feels 13 degrees cooler because you don't even have to sweat. The humidity is pulled out of your skin. The air is so dry, and it makes you feel cooler. So this is a very important thing um, to remember. I said if it's really humid outside, you have to make sure you're drinking plenty of water and you're just not being outside too much because you do not want heat exhaustion or heat stroke. You can die from it. There have been lots of football players who have died because their body temperature is raised. A famous one was a Minnesota Vikings player. So a professional football player, Corey Stringer, actually died because of this. It was a really hot year in Minnesota where they had training camp. It was like 90 or 95, but it was a really high humidity, and then he had his helmet on, and his body temperature just raised up because he didn't have enough fluids, and his sweat wouldn't evaporate. So this is a huge thing. You need to make sure you kind of pay attention to this. So heat index when it feels hotter than it actually is because of the humidity. It won't let your sweat evaporate.